Welcome back to Power Live for our final session for the GAN channel and for the whole event.
We're closing today with an open panel discussion on gallium nitride and wideband gap technologies. We've been receiving your questions over the past couple of weeks, and we are pleased to welcome our panel of experts who are ready to address the topics you wanted us to discuss. Moderating our panel today is Maurizio Di Paolo Emilio, Editor-in-Chief at Power Electronics News. I'll hand over to you now, Maurizio, to introduce the rest of the panel.
Thank you. Hi, everyone, and welcome to this panel discussion about GAN, about gallium nitride. I am Maurizio, Editor-in-Chief of Power Electronics News, and today I'm very excited to be here with great speakers to talk about GAN. So we are going to share with you some great topics to our panel, but let me introduce the speakers. So I am here together with Caroline O'Brien, so CEO at Qubos Semiconductors, Temok Rodriguez, Chief Engineering at Ricardo, Michael Bjork, CEO at Hexagem, Dilder Chowdhury, Director of Strategic Marketing at Nexperia, and Jim Ani, again, Applications Director at Nexperia. Hi, everyone, and thanks a lot for coming on. So, over the course, we will look at the GAN, so at the GAN itself, and understand a bit more about technical features, about how it can be used, but also applications, market applications, how it's moving forward in various markets. But before that, I would like to involve each of you, the speakers, to say hello, to give us a little bit of your background. So, where you come from, what's your job, involvement in this field? So, Caroline, hi, Caroline. Thank you for coming on, and so please introduce yourself.
Hi, Maurizio. Yeah, it's great to be here at the Nexperia panel live session and to join everybody for the GAN discussion today. For myself, I've spent 30 years nearly in semiconductors, mainly in silicon. My early career, I was actually in a power semiconductor company. But more recently, I joined Qubos as CEO to commercialize the technology and bring new technology to market. Qubos is developing a new technology and new material called cubic gallium nitride. So it's the cubic form of gallium nitride. And previously, it's been a challenge to produce cubic gallium nitride. And Qubos can not only produce it on large-scale wafers, 150 millimeters and above, but potentially we can scale to higher wafer sizes, but we can slot seamlessly into existing production lines. Now, today, we're focusing on visible light and LED market and solving what's been known in the LED industry as the green gap. So this is where there are inefficiencies in LEDs in the green wavelengths. And so Qubos can solve that problem, and also a problem with scaling down red micro LEDs in displays. But we're hoping that's just the starting point.
Thank you, Caroline. So, Temok, do you want to give us a little bit of your background?
Where of course.
You come from?
Yeah, thank you. Thank you, Maurizio. Yes, very pleased to be here talking to everyone. I've been working in power electronics for 20 years. I started in renewable power, as it happens, designing power converters for converting DC energy from solar panels and feeding that energy into the grid. And at the time, if you go back 20 years, we had MOSFETs, silicon MOSFETs, we had a CoolMOS coming into the market, we had IGBTs, and that's how we would design power converters. And we started cranking up power, from a few kilowatts from smaller inverters into larger and larger power converters for larger solar farms. And coming from Cambridge University, when I finished, some of my colleagues then went on to the wind industry, where they were doing several hundreds of kilowatts of power conversion to get the energy from the machines. And now, of course, those wind turbines range in the megawatts. And of course, they use the larger the IGBTs and so on. And through the last 10 years, we've seen that revolution of wide bandgap devices with silicon carbide going mainstream essentially, and And now that I'm with Ricardo, I've seen that in the automotive industry with companies like Tesla, who migrated their traction inverter drive from IGBTs onto silicon carbide, and we're the first company to do so. And now many other companies are jumping onto the bandwagon. And of course, now we are onto the next revolution, which is GAN, which promises to increase efficiency and allow us to reduce the size and weight of power converters. And now it's all a matter of convincing the end customers that the technology is mature, is reliable enough to start rolling it out in earnest. My job at Ricardo at the moment is to grow Ricardo's electrification agenda with wide bandgap devices, either silicon carbide or gallium nitride, and each has its own applications based on voltages and power levels, and both will have to coexist. And today, of course, it's all about gallium nitride, and hopefully I can give you an insight on how we see gallium nitride rolling out into the automotive sector.
Yeah, and we will talk in a bit. Thank you, Temok. Michael, hi Michael. Please tell us more about you.
Hello, it's great to be on this panel as well. My background is I have a PhD in semiconductor physics, about 20 years experience in materials development and characterization. And it's mainly on the materials development, mainly epitaxy of 3.5s on silicon and nitrides. And I spent a lot of time on selective epitaxy on really nanostructured surfaces and 3D materials. Looking at various application areas ranging from low power CMOS through photovoltaics, UV LEDs, and since about a year and a half, I'm working with Hexagem, which is a small startup in Sweden on power electronics, where we are developing, or we have a solution for high quality GaN on silicon. So we believe we can merge or close the gap between bulk GaN properties and the cost and scaling advantages of GaN on silicon. So,
thank you, Michael. So, and then we have our Nexperia guys, Dilder. Hi, Dilder. Please introduce yourself.
Yeah, hi, Maurizio. It's nice to be here with this panel for discussing about the exciting material, gallium nitride. I had my PhD from Manchester on the 3.5 materials based on the MB grown superlattice structure. And then it's nearly 30 years now in semiconductor industry, especially with the Philips, NXP, and Nexperia. I've got 25 years here working from 1200 volt, 800 volt, and they're down to 20 volt. So wide range of silicon devices, and coming back to my 3.5 in wide bandgap material in the power GaN programs. So I've been from the beginning of the power GaN program with the because we've been working on power GaN devices for last 10 years. And I've been in different role. Currently, director of strategic marketing I bring lots of technical know-how within the industry, and we are working on mainly medium to higher power in GaN, where the biggest benefit we can see here. And I'm very excited to be here to discuss about this one. Thank you.
Thank you, Dilder. And Jim, tell us more about your background.
Yeah, good morning. My name's Jim Honey. I'm Director of Applications for the GaN product line for Nexperia, located in Goleta, California. And yeah, pleased to be here. I'm a circuit designer by trade. Actually started off as an IC designer with GE in the early 80s. Was able to work on the very first 600 volt HVICs. And then took a 23-year break from semiconductors to just be a circuit designer for various companies. And then 2007 got back into semiconductors with a GaN company here in California. And then as of 3 years ago, I've been working with Nexperia in applications.
Thank you, Jim. Excellent. So thank you, everyone, and so it's going to be a great panel about GAN. So GAN, as you know, is let me introduce my first topic. Is a wide bandgap semiconductor and is working very well in several markets. I would like to understand better with your help in terms of applications. So as a material, GAN, as you know, appears to have significant inbuilt advantages over silicon. I guess for many applications, I guess that we know better that the gallium nitride is important, is better than silicon. There are clearly many market applications where that benefit from GAN. I can mention power converters in consumer, industrial, and other markets such as automotive, motor control space. This is also connected with the features to the band gap 3 times higher than that silicon, and moreover, GAN increases also not only the efficiency of power conversion stages, but also giving a smaller dimension, lower weight, and lower overall cost. Let me share this question. Which applications are now emerging for GAN, and where we can expect the next wave of GAN, the next wave of growth in terms of cost? Because we need also to check what means cost in this case, because there are a lot of things that we need to put in evidence. So, Caroline, if you want to take for first, and then we can follow with others, Temok, Michael, and others. So what's your comment in terms of applications?
Yeah, I think in terms of applications, obviously with the improvements in terms of being able to have smaller design footprints and because of the efficiencies of GAN, I think this enables applications which haven't been able to be recognized or widespread before, things like picocells and small base stations, and repeaters that are frequent rather than filling larger spaces. So I think there's a real opportunity there for the smaller system design overall, and that opens up new and exciting opportunities of where such applications can be developed.
Thank you. So, Temok, tell me your comment. If I have to ask the following statement, so GAN is here to stay, and why? So, what will be the strongest case, the most important application from your experience, also with respect to its position against silicon?
Yeah, absolutely. I think Caroline put her finger on the main advantage, which is higher power density. But many of you, hopefully out there at home or work, will have seen those charts of power versus switching frequency and what technology fits better where. And in the early days of GAN, they were positioning GAN on the higher frequency and low power applications. So DC-DC converters of 1 kilowatt up to maybe 5-10 kilowatt range. And that is a sort of market, and that can go into telecom, that can go into energy generation, it can go into consumer electronics, and so on. A myriad of applications around DC-DC converters to make them more efficient and save energy. Right? We want our energy to come from renewable resources, and therefore it's important that we look after it and generate the least amount of losses. And GAN will give us that because it can reduce switching losses, and I'll go into that in a minute. If I'm allowed to go into the more automotive context, as you see in your screens there with that slide, this is the roadmap as we see it at Ricardo at the moment, and the agenda that we are pushing out there and convincing our customers and OEMs to go through. And you can see 2 large applications. So on the left-hand side, you can see onboard chargers and DC-DC converters. And usually they're bundled together because there's in an onboard charger, there's a DC-DC converter in addition of an AC to DC converter, a rectifier, essentially, a power factor corrected rectifier. And that is the most obvious application of where GAN will go, because it's in the lower power range. So at the moment, your onboard charger will do 3.3 kilowatts, maybe 7 kilowatts, moving towards the 11 kilowatts if you have 2 phases or 3 phases available at work or at home or there's a charging station, and progressing towards the 22 kilowatts. So that's starting to stress GAN devices a little bit at the moment. And for those who are familiar with GANs available, commercially available, the current ratings aren't there compared to silicon carbide or IGBTs. And that's what's limiting how much power you can put through them. And it's also driving circuit designers to start looking at paralleling devices and that sort of thing. So we'll definitely start with DC-DC converters. We can easily imagine the first application to be a 400 volt to 12 volt DC-DC converter. So this will be the one that takes power from your high voltage battery and charges your 12 voltage battery and keeps it topped up. That's doable. It can be done today. We have automotive qualified devices to do it, and it's in the right power range. The next level up will be, increasing that power level to 5 kilowatts or so on. And the real challenge then becomes when the automotive industry moves towards an 800 volt battery system, right? Because your commercially available devices cannot handle that voltage. And you'll have to be creative, or the semiconductor industry will have to catch up and release the devices that are higher voltage rated. And maybe the rest of the panel can comment on that. So that is onboard charging, DC-DC converters. On the right-hand side, if we can go to the previous slide, please, the first slide. On the right-hand side of that slide, you see traction inverters. Now, up to 2 years ago, no one thought that GAN was suitable for traction inverters because of the power rating. When you talk about traction inverters, even the smallest car, like a Volkswagen E-Up, uses a 60 kilowatt motor, right? So that's quite a lot of power for GAN. So you need to start thinking how can you put GAN devices together to get to that power rating. So you start looking at putting them in parallel. You start looking at creating a module for handling that level of current. And still you have to keep it at 400 volts, right? Because that's what the current devices can handle. But we know that the industry is going towards 800 volts. So we and Ricardo are now looking at multi-level inverters using GAN because we know the advantages of it, and just taking us to that 800 volt level, which then will enable higher powers because you double your voltage, but you keep your currents low, right? So your transistors can handle it. And of course, we want to roll out GAN to as many applications as possible because we want to save energy and increase the range of our vehicles. And ultimately, we need to get to 100 kilowatts, 150, 200 kilowatts power level, right? And we'll only get there by either the semiconductors being designed for high voltage in combination with the creation of power modules.
Okay, so get back you with a couple of questions about what you mentioned. Let me move forward with Michael about tell me about your comment in terms of applications. So in terms of analysts, we know that I have read several papers for analysts that is providing just several studies in terms of what is the market GAN technology in terms of billion. So I don't remember how many billion in terms of dollar. And the total GAN market is for sure increasing with a good rate for the next years, 5 years more or less. And the GAN consumer power supply market should be the main driver. Based on this research, I can say that also by entering the power fast charger market, GAN will shift for sure to high volume production. So tell me, just to add this one to my questions early. Tell me your comment, Michael.
So in terms of applications, just to tie it back to Temak, what you said, I think we are looking at higher and higher requirements in terms of voltages and voltage ratings, and also, of course, to put this in production and getting the cost structure down, we need to go to, at the moment, mostly it's 150 millimeter wafers, but in the future, scaling this up to 200 millimeter wafers, and who knows, probably there will be attempts at 300 millimeter wafers. So that puts a lot of requirements on the development of materials, of course.
Excellent. Tell me.
Yeah, and so basically, GaN on silicon, this is, of course, this is where you have the cost structure and the scalability. And so probably most of you in the audience knows that it's not straightforward to grow GaN on silicon. So it's basically two main problems. You have gallium nitride and silicon have quite a different lattice constants, so they don't match. So you need to grow quite advanced stacks of different layers before you can fit GaN on silicon. And even if you do this, you will create a lot of defects, dislocations that are detrimental. It will cause leakage and premature breakdown. The other problem is there is also a thermal expansion mismatch between GaN and silicon. So when you grow this at around 1,000 degrees, when cooling, these two materials, they shrink by different amounts, and you may end up cracking the GaN or having too large wafer bow to be able to process devices on them. And maybe I could then, if you can show, I prepared a slide on this, if this can be shown, maybe I can introduce what Hexagem's solutions to this problem is, so looking in the future. So what you see on this slide, we're developing a technology where if you look at the schematic and the images below, you see we are basically on a silicon wafer, which has a very thin buffer, sort of a conventional buffer of aluminum nitride and GaN. It only needs to be a few hundred nanometers and very poor quality. Patterning this surface, basically opening up small, tiny holes to the GaN surface, we can grow with EPI these gallium nitride pillars that you see. And these are basically, what this means when you grow in these small openings, you filter out all the dislocation that you have in the underlying buffer layer. So basically these GaN pillars are defect-free. You can see that in there's an example where a lot of arrows pointing to dislocations in the buffer, and they don't penetrate through into the GaN pillars. And then we've developed a method to basically merge these pillars back into a planar layer. And then we can grow planar EPI on top of this, whatever device layers that is needed. We are currently working on doing this. We can do it on sapphire, we can do it on silicon carbide, of course, on silicon, which is the main interest. This is still pretty early days, but we are sort of mid E8 in terms of dislocation densities on silicon. We are targeting really, as I mentioned at the beginning, to try to close the gap to bulk GaN. So the immediate targets are to go below mid E7, which we think we can do pretty short term. But also what's interesting is we think this technology with what we call coalescence, when we merge these pillars, is that we will enable thick drift layers as well, or thick GaN layers on silicon, and still keep the bow within what is within requirements from the later on processes. So this we can do, it's a particular state of where we can manipulate the stress in this coalescence layer to allow thick layers. So we also think this would be a really great material for vertical devices. And maybe there are comments about vertical devices from the rest of the panel, but I think it has advantages in terms of real estate, sort of you can get smaller devices, higher breakdown voltage, etc.
Thank you. Okay, before comment this part, Dilder and Jim, tell me your comments. I can let me add just one thing. So the GaN with zero reverse recovery charge allows to be used in topologies that were not previously considered for power supplies. And with these new topologies can help to achieve new level of performance. What kind of new power conversion technology we can find just by using GAN FETs that we can enable. So I can think in terms of bridgeless totem pole PFC under CCM, continuous conduction mode, where using superjunction MOSFET are not practical due to the high reverse recovery losses. And in this case, GAN FETs can be a plus in terms of applications. Also, in terms of new degree of design flexibility that can offer for not only automotive, as Temok mentioned, but also for other markets such as motor control. And this is also several improvements to guarantee the strong adoption of GAN for the next future. So Dilder and then Jim.
I think it's probably more suitable for Jim, but I'll just start here. Yeah, go ahead, Jim.
Okay, Jim.
And then I'll take it up.
Okay. Yeah, well, you highlighted a really critical application or topology, which is the bridgeless totem pole. Just a very elegant, simple way to do power factor correction that requires a FET that can operate in continuous conduction mode with very low recovery loss. There's a bit of a debate on whether it's correct to say GAN has zero. There is always capacitive charge, which strictly speaking is part of the recovery. But the point is it works, whereas superjunction silicon MOSFET with this massive body diode is just not really a viable solution. Other topologies, any inverter topology, you almost always have various phase angles of the output current where you need to be able to tolerate, current coming backwards. Those are great applications. One that I would mention, Temok is addressed automotive, which is definitely key. The onboard chargers, the DC-DC, the traction inverters, auxiliary inverters, great applications. But the development of large batteries for electric vehicles is creating a lot of applications that in the past nobody thought of as portable power. And suddenly we've got this great industry of lightweight, high-powered, high-energy density batteries. And people are thinking, well, yeah, that could be portable power too, without a gasoline engine. And that's an interesting place. Again, that an inverter is the logical building block there, but because you need to charge that battery at times, it needs to be a bidirectional inverter. Therefore, a totem pole PFC essentially is an inverter running in the opposite direction.
Okay.
Those are the applications I would see. Dilder, have I missed anything?
Yeah, and just to compliment, obviously Jim and Timok actually already covered most of them. As the motor control is one other area because of the low QRR or virtually absence of the QRR helps lower filter designs. So the designs are much more simpler. And some of the switching waveforms are actually counterintuitive, almost like when you have got a very fast device, but you don't have a huge overshoot. Because of the absence of the QRR, that makes the switchings really good. And obviously, you probably, those of you have missed our GAN Power Live there were 4 sessions just before this one, where the paralleling of the GAN, the double pulse test, the switching waveforms actually greatly covered that how the GAN turn-off losses virtually very close to zero, and the turn-on losses that you can control with your RG. So the switching losses are so low, and because the higher mobility of the GAN and also the transfer characteristics of the GAN such that the switching losses are really low. And that makes these bridgeless totem pole as ideal applications. But all the other applications, including the soft switching, actually where we have demonstrated that the GAN switching losses is significantly low compared to the silicon carbide or other contemporary devices. And so, yeah, GaN has a future, very good. And most of the applications that currently running, GaN can fit in very well. In addition, it's actually opening some of the opportunities which wasn't possible. So I would think there will be a coexistence of multiple technology along with new opportunities that GaN starts opening up because of this particular behavior.
Good. Thank you, Dilder. So you mentioned also an important application about automotive. So as the automotive industry moves towards zero-emission transportation, manufacturers are rapidly ramping up their electrification program. This is important also for GaN. Another range of topic that I would like to share with you, also to connect with what Temok said, in terms of powertrain, in terms of electric vehicle, in terms of packaging, and in terms of GaN epitaxial films. So the conversion to GaN is well underway, but of course there are also technological challenges. I can say that so a play in terms of chemistry and physics to guarantee the best approach for the next future of GaN. So Caroline, can you tell me also what are you doing in terms of your company?
Yeah, no, I mean, obviously we're a little bit further down the road, even than Michael introducing his GaN on silicon technology. And, you know, I have to caveat this because we haven't done as much work in the power semiconductors as we'd like. But there are some interesting differences, fundamental differences between hexagonal gallium nitride and also cubic gallium nitride. And, you know, this is to the higher electron and hole mobility. Which potentially, you know, has positive effects again for vertical devices. So it's interesting that Michael spoke about that as well. You know, but you know, I think the symmetry, and as the slide shows, for cubic GaN, the symmetry does change some of the dynamics of the material and offers opportunity in the future. And I think as you go forward with markets, you know, early in markets, platforms get used multiple times, and then as markets become more specific and more refined, then we find that the needs change and the needs become much more detailed and much more prescriptive for certain applications, particularly as they become very large, because the markets then demand specific solutions. And so we can see there's an opportunity in the future for new materials, but also for hybrid solutions. We grow on 001 silicon, which has potential for you to also add in the future, you know, silicon devices as a hybrid with GaN devices. And I'm sure, you know, at Hexagem as well, Michael's thought about those opportunities as well. So you end up then be coming up with sort of application-specific type devices rather than generic or more generic solutions.
So Temok, you mentioned, please correct me, GaN onboard charger. In terms of powertrain. So this is a good opportunity for GaN, which is very well positioned to penetrate also the lower power charger range. I mean, 3 kilowatt to several 10 of kilowatt. Please correct me. Another one, so starting from 2022, I guess, is expected to penetrate the 48 to 12 volt DC-DC converters. Where we should see a trend towards to standardize the 48 volt systems. So, and in terms of wide bandgap semiconductors, we can mention also silicon carbide, not only GaN. So, if you can tell me just advantages, disadvantages about this both.
Yeah, of course. I mean, I'll address your first point, which is the standardization of voltages. I'm yet to see that. Many OEMs are sticking with 12 volts, even though we tell them that it's more efficient to go to 24 volts or 48 volts. And some cars will have multiple voltages, you know, in the safe voltage, if you like, range 24 volts, 48 volts. and they'll be running, for example, cooling pumps at 48 volts because it's more efficient, and then the rest of the accessories at 12 volts because that's what we've always used. And there's a vast supply chain of accessories for the car that are 12 volts. You do not want to migrate to 48 volts because that would be quite a lot of effort globally. I think the challenge for GAN, specifically on OBCs, is that input stage here in Europe could reach fairly high voltages. So for a single phase, it's fine because you get to 400 volts, 500 volts, your 600 volt devices will do it. But for a three-phase system, the input stage will go up to 800 volts, 700 volts, thereabouts. And then you need to start being creative as to what topology you want to use on that front end of the power factor correction. Having said that, most of the vehicles will be single-phase charging, and therefore GAN is perfectly suited for that. Now to your second point, which is silicon carbide versus GAN. If the studio staff can show us the second slide from Ricardo, I can make the point. And we've been working with silicon carbide for many years now, and we have our own traction inverter that we offer our customers. And when we started looking at GAN, we did this exercise where we do a lot of digital twin modeling, and we validate those models against the hardware that we build, and then make sure that the models are correct. And then we have one for silicon carbide, and we recreated that for gallium nitride for a 30 kilowatt application, which we thought maybe GAN can get us there at 30 kilowatts, right? And these are the sort of numbers that we came out of that simulation, where you can see that silicon carbide was peaking at around 97.4%, and GAN was taking us higher to the 98.1%. And there's some metrics on gravimetric and volumetric power density, which are all right. They are not groundbreaking, but they are fairly good anyway because of the wide bandgap devices. I think the most eye-catching graphic here are those pie charts on how the losses distribute, and that is brilliant because it shows you that in silicon carbide, you can design your converter to roughly have equal, switching losses and conduction losses. In this case, most of the losses are switching, 63%, with the rest being conduction losses. But in the gallium nitride inverter, it swaps, and it swaps with quite a lot of bias as well towards conduction losses. So in other words, your switching losses are almost eliminated, and you end up with a lot of conduction losses, which of course, these come from multiple things, like bus bars and PCB power planes and whatnot. But there's the conduction loss on the device itself. Now, of course, at this point, you can, as a designer, you can decide to then parallel the device if you have the real estate and the cost budget for that component, and that would bring down your conduction loss without impacting much on your switching loss. Whereas you cannot do that with silicon carbide. If you parallel devices, your switching losses are there. In fact, you make them worse by paralleling devices. So that's a key selling point for gallium nitride, and why I think it will be the technology to dominate in the coming future.
Thank you, Temo. So, Michael, you mentioned gallium on silicon platform just before earlier during your introduction. So if we focus on the various substrates in power GaN, these GaN on silicon represent the larger portion of the market. So we can say that gallium on silicon is the platform for automotive applications. And in terms of wafer, 6 inches, 8 inches. So as you said, I think, so if the wafer would increase in terms of size, this would be also a challenge in terms of mismatching, as you said, and we need to compensate. So we need, so some challenges on epitaxial need to be solved with, complex structures to compensate the mismatching of thermal coefficient. And so this is due, I guess, because GaN is grow on heterogeneous silicon substrate. What are the challenges?
Yeah, so it's sort of what we discussed earlier, that to grow the GAN on silicon, larger and larger wafers, basically when you grow this because of the thermal mismatch, when you grow a stack on silicon, you will stress the GAN when you cool it down, and you will create a curvature, a bow basically. And of course, if you have the same design and you scale the wafer, the curvature is the same, but of course then the bow will be larger for the larger diameter. So you need to adapt the stacks and make them more and more complex to accommodate the bow requirements on larger wafers. And well, I do believe there are solutions. We have a solution for this. There might be others around, but with this coalescence approach, basically we can lower the dislocations, which is will increase breakdown voltages. But there is also, I cannot go into why that is and how we do it, but during the coalescence, we have unique ways of manipulating the stress. So basically, we only need the thin, say, 100 to 400 nanometer coalescence layer to set the stress. And basically, with modeling we're doing comparing to experiments, we are not quite yet at those wafer dimensions, but the model we can predict, and on smaller scale, it agrees well with what we observe. We should be able to get really thick GAN on silicon, basically. So for the standard lateral devices, but we also think it will be very suitable for vertical architectures. Yeah.
So I have a question for Dilder from the community. So please tell me if there is a segregation now and future according to application devices of power devices such as IGBT, GaN, silicon carbide, and gallium trioxide in automotive.
Yeah, as I mentioned in the previous comment, there is a coexistence of this one, but there will be overlap. So there are areas of applications where obviously cost performance will decide exactly where do you want to position. But there are a few applications where actually GaN has got a unique position. Just for example, if we say the 80 plus titanium grade, so where the GaN kind of taking the very high-end, top-end position where the highest efficiency, lowest power losses are required. So, and there are higher frequency applications where the GaN will take the field, where the IGBT probably will be limited. So for example, even in the traction inverter, the IGBT is almost limited to say 8 to 10 kilohertz, whereas GaN, some of the demo or the early eval version of the traction inverter, people are working on 30, 40 kilohertz already, and which will obviously puts lots of challenges to the motor manufacturers as well. So the better the electric motor improvement also happens, and that can also, those both development will go in parallel, and the GaN will pose lots of challenges to the existing infrastructure, and then the infrastructure will develop to catch up with the GaN. GaN is not the limiting factor at the moment, but it's just giving the opportunity so that other applications can come up. Say, for example, the higher application, you need a high current, high power inductors, which is in itself is a challenge. What core materials you are going to, so that you'll have to improve the inductor. And so the GaN will start taking some of those new opportunity and new possibility that it's creating. Absolutely.
Thank you, Dilder. So I have a couple of questions. So let me share with Jim in terms of paralleling GaN FETs. So in your opinion, what is the reachable limit by paralleling GaN devices? How can equal current sharing be achieved when multiple GaN FETs are connected in parallel? And also, in terms of the next challenges for paralleling GaN. I guess that the talk of today will be also very nice to explain this part. Jim.
Yeah, indeed. Our colleague Scott Durkin had a presentation today on paralleling GaN FETs, and yeah, he was showing over 100 amps with two of our 39 milliohms in parallel. And yeah, I don't think there's a limit. One of the interesting things with GAN is, we can scale the die sizes. So as we look at these traction inverters, how do you get hundreds of amps? We've done that with 4 and 5 of our existing parts in parallel, say 33 milliohm parts, put those in parallel to get, a couple hundred amps. But there's really no limitation on making large dies. Dilder's been active in those studies of at what point is it more efficient to stop making the die bigger and just parallel 2 or 3. I don't think there's you're asking about a limit. Obviously, we're looking at traction inverters and thinking that's a good application. Initially, the more modest, 100 kilowatt kind of range makes sense. But even there, you're looking at hundreds of amps, and T-Mock could elaborate on, the vehicle has to climb a curb or something. Even a pretty small vehicle draws a lot of current momentarily. So, but we're thinking those are good GAN applications. Paralleling, it takes a little thought, make sure everything is symmetrical and decoupled, right? You're creating lots of resonances when you put parts in parallel. And that's not a unique GAN issue. It's really just a high-speed switch, right? If the industry wants fast switches, by definition, you have gain at frequencies you didn't in the past. Suddenly, all these parasitic L's and C's are feedback elements. In the past, you ignored them. It was a little ringing and nothing worse. Now they're potentially contributing to an active resonance. That's the issue. It's like I said, it's not a GAN issue. It's just a high-speed switch issue. You put those in parallel, you multiply the resonances, and you just have to make sure you're not exciting them and amplifying them. And so, just some common sense decoupling, symmetric layouts, clean layouts. We've been able to parallel, like I said, 4 and 5 dies, and it's not an obvious technical limit. It more becomes one of economics and assembling what makes sense to do.
Thank you, Jim. So we have less 15 minutes. So I would like just to share my last questions for everyone, and if someone wants to take to comment. So the first one is in terms of supply chain. So we are seeing a lot of applications, and markets require even more GAN devices. You explain better. So are there major supply chain challenges for GAN market penetration to succeed in the way? Also considering this period in terms of COVID pandemic that is improving, I hope, I think. But so when we also in terms of general market for electronics, I just was reading an article yesterday, I guess, with the title. So this was in Italian, a title about getting the vaccine for the supply chain, just to solve the problems that we could have, not only in terms of GAN, because the markets require even more GAN, but also in general. So just a comment in terms of supply chain from your experience, like leaders in the market. Who wants to comment?
Yeah, I can start on that one. Obviously, one of the biggest benefit of the GAN on silicon is because it's grown on silicon substrates. So at the moment, it's 150 millimeter, and there are work ongoing to move into 200 millimeter. And most of the reactors currently actually accommodate 150 and 200 both. So from that context, actually increasing the number of reactors can increase the initial supply material for the fab. From the fab point of view, there are many silicon fabs around the globe, right? And it is a lot more easier to increase the capacity within the existing silicon fab. And the GAN processing is very much like silicon-like processing, And that's what we do within the silicon fabs. That helps the volume, basically within the supply chain, the volume manufacturing. We have got multiple fabs, and if required, obviously the more and more automotive requirements means a huge amount of electrification, and semiconductor areas would be required. And from that context, I think GaN is a much better, especially GaN on silicon is a much better position. And obviously for the back end, in the die level or in the packaging level, we have got the vertical organization where we have got our own packaging in a multiple site in China and around the globe, and which allow to have a volume production, especially for the packaged devices. And for the die level, obviously, we are investing quite a lot to increase the capacity as and when it would be required. So I hope this gives the initial understanding the supply chain challenges that we are trying to handle.
Thank you, Dilder. Any other comments?
Yeah, I'm happy to comment, Maurizio, because I was in the industry in silicon semiconductors when the industry went fabless in around about 2000, and it seemed to happen almost overnight, which it obviously didn't. But the looking back at it now, was actually in quite a short order, and that was with obviously a huge increase in demand, particularly in consumer electronics and mobile phones, etc. And I can see this is on the horizon, excitingly, for gallium nitride and GaN products, and that's why we're here today. So as this happens, and there's a catalyst in the market for more demand, the suppliers obviously need to react, and you can see some of that coming into play. Still, they said, you can see that the supply chains are rallying in the right direction, but this could happen quickly. I think the industry does need to prepare, whether it's going to be, vertically integrated supply chains or whether it's going to be pure play foundry. And in compound semiconductors generally, there's a lot more pure play foundry type models coming up. So I'm watching with real interest to see how it's going to unfold, and there will be a time where both models work very well, but if it happens like the silicon semiconductor industry, one will win out over the other.
Thank you. So we have just 5 minutes, so I have just a question, I guess, for Jim or Dilder in terms of RDS on. Can RDS on of GaN-based power devices be further reduced, or we are approaching its theoretical limit?
Absolutely. I'm not sure we'll be able to reach the theoretical limit, but at the moment we are actually already in our 3rd generation and managed to get devices below 5 million. And then in our next generation, we are already hoping about 20-30% reduction in the RDS on. And one of the advantages of our GaN program, what we are seeing is the defectivity level is already in the CMOS level, which allow the larger die solutions, as Jim already alluded to. That's why that about if you go down to around 2 million, where you'll be able to bring a lots of power out of that one. Currently, you probably need about 3 die in parallel. Probably you can go down to 2 die in parallel, even to get in excess of 100 kilowatt kind of power. And obviously, there is a trade-off between the RDS on and the die size, RDS on die size and multiple die in parallel, because the yield factor is quite critical. Sometimes 2 die in parallel probably is cheaper than having a very large die with a lower yield. Yes, so there is no limit at the moment.
So thank you. So we are in conclusion, but so just very fast, each of you, just a recap in terms of also what are your next projects, and if you would like also to put in evidence what we didn't cover. So we can start with Caroline and following the line with others.
Yeah, no, thanks, Maurizio. Yeah, so effectively, we're focusing on LEDs for today and solving the green gap issue, and obviously red micro LEDs for displays. But I do hope that we get opportunity to talk about materials for power devices in the near future.
Thank you, Caroline. Temuk.
Yeah, I think I alluded to it earlier. Essentially, we are Ricardo, we are a technology company. We want to enable future vehicles and electrification. So for us, it's about pushing that technology boundary. So it's putting more power into those traction inverters, getting to the 100 kilowatt mark. If we can get higher, even better, and then demonstrating that in vehicles. And hopefully that paves the road for high power GAN.
Thank you. Michael?
So basically we are pushing for getting much better quality GAN on silicon wafers and to larger and larger wafer diameters. Of course, as we are developing a material, we're happy to have any application on it, so not application specific, but we think we have good potential applications both for a standard GAN and also vertical devices, if that is of interest in the field. Thanks.
Thank you, Michael. So Dilder and then Jim.
Currently, obviously, we are working on a copper clip version of the GAN technology to complement the best performance of the semiconductor to put it in a best package. So this is one area which is quite exciting. And then a very low RDS(on), almost close to 10-12 million, we can do packaged now already, which is we are working on. And we are also going beyond a lower RDS(on) devices for the traction inverter. And considering from say 25 to 30 kilowatt right up to say 120, 30 kilowatt, where is the whole of the automotive volume market for the everyone. If we forget about the top end, the high power, high end market, the GAN is very well positioned to support those areas.
Thank you, Dilder. And Jim?
Yeah, for our applications team, a lot of the work is just helping design engineers realize topologies that have been well discussed for years now. You're getting a totem pole PFC and just, not just understanding that it's possible, but actually get a successful design in the field. A little more forward thinking, one of the exciting options or possibilities for the applications is rethinking what are the best choices of topologies. And one example, we talked about the hard switching, continuous conduction mode. But for resonant applications, which are nominally soft switching, very common, you'd say, okay, it's an LLC and make sure that it absolutely positively never goes into hard switching. Well, with GAN, you can lighten up that requirement. Say, okay, it can go into hard switching. Let's think about a topology where it's mostly soft switching, but it doesn't have to always be. What does that make easier? What does that allow us to do with the topology? And one final comment, I want to hit up Carolyn and Michael about giving us a die with both polar and semi-polar planes so that we can make a single chip opto-isolated FET. I would love to have that. Thanks very much.
Okay. Thank you, Jim. And thank you, everyone. We are in conclusion. We talked a lot about GAN. So it's been a pleasure to talk with you, to know more about gallium nitride technology. I want to thank Nexperia for having me in this panel, and congratulations also for the power event during the last 3 days. Thank you, everyone, and so stay tuned. And so, Dilder, if you want to add something.
No, it's fine. Thank you very much, Evan.
Okay, for the talks, in terms that all talks of Nexperia are on demand, I guess.
Yes, right. Okay, yeah. Thank you for that one. Yeah, there had been 4 presentation today before this panel discussion. All of them are on demand available in our Nexperia site, and there are some exciting materials, especially very much GAN specific, and would be very, very beneficial for the young designers and to the experienced designer, for all of them. And there are lots of very great materials available there.
Thank you. Thank you, everyone. Bye. Thanks.
Thank you. Bye-bye.
Thanks.
Thank you, Maurizio, and our panel expert. Great discussion and very insightful. So this brings us to the end of our live broadcast for Power Live 2021, and what a 3 days it has been. We hope you enjoyed watching and participating as much as we have enjoyed presenting our latest innovation topics to you. All of the live sessions, as also mentioned from this week, are recorded and will be available to watch on demand on this event platform as of tomorrow. Don't forget, you can also still watch our demo videos across all 3 channels.
Thanks again for joining us, and have a great rest of your day. On behalf of all of us at Nexperia, we're looking forward to staying in touch with you.
See you next time.